Here we go, L'Hopital's rule, example 3, part B. We're taking the limit of a fraction, which again always opens up the possibility of L'Hopital's rule. But we got to check to see, well, maybe if we just stick the number in, we'll get a number, right? So what I always do is I check the denominator first. And so 5 times 0 would indeed be 0. So far it appears that we're indeterminate. Who knows? Because we need to check the numerator as well. Let me throw this out there. If we get a number other than 0, 12 divided by 0 does not exist. That would be it. But we need to check to see what that numerator would be. And if it's also 0, then we do L'Hopital's rule. So put 0 in for x up here. 4 times 0 is 0. 0 plus 1 is 1. Square root of 1 is 1. Then we ask ourselves, what's the natural log of 1? Now that's a thing, if you think hard enough, you know what it is. But if you have to, you can grab this beautiful machine, hit that there natural log function, put in a 1, natural log of 1, and it's 0. All right? I would like it if your brain knew that, but let's backtrack again. 4 times 0 is 0, plus 1 is 1, square root of 1 is 1, and natural log of 1 is 0. It's indeterminate. Derivative. All right, now, here's the thing that you hopefully would remember from the previous assignment. If we want to take the derivative of the natural log of something, it would be beneficial to us. I'm not doing derivative yet, you'll notice, because if I want to differentiate something that has a square root involved, it would be beneficial to change that into the 1/2 power, wouldn't it? Whenever you take a derivative or an integral, it's typically beneficial to change radicals into fractional exponents. So there we go with that. I hope you also remember from the previous assignment that if we have the natural log of something to a power, this is still more algebra going on here. So we're just rewriting this thing before we prescribe L'Hopital. See, we're preparing this to take its derivative, f prime. So I'm not doing L'Hopital yet. Can't we bring that 1/2 in front as we did on a previous assignment? So we're preparing that numerator using the algebraic properties of logarithms to prepare it for differentiation. More algebra that I would suggest. I think that 1/2 there, you might as well move the 2 down underneath with the 5. You can leave the 1 up here and move the 2 down there. I still think that's all smart algebra there. So, look, I know our time together is almost done. One more time, probably won't be the last time. It's just the algebra. So, then the next thing I think would be to leave the 1 up here, move the 2 down there. So the 2 times the 5x changes that to a 10x. And then we have natural log of 1 plus 4x. So that's all just algebra rewrite of that expression in order to prepare this to take the derivative and apply L'Hopital's rule. Now we'll do L'Hopital's rule. So the derivative of 10x is 10, which bodes well. I'm thinking a step ahead. Won't that denominator be 10? There's no more x down there, right? I don't think it's going to be indeterminate. Next step. Derivative of this. Chain. Natural log. That'll be 1 over 1 plus 4x. And then the derivative of what's inside, which would be 4. Awesome. So this is the derivative of that numerator. And I'll remind you, we took the derivatives of these individually because it was indeterminate back here. All right, now if we put 0 in for x, well, the denominator is 10 up here. That'd be 0 plus 1. 1 over 1 is 1, and 1 times 4 is 4. 4/10. Reduces to 2/5. Wow. So, yeah, obviously there's a lot of algebra going on there. There was some calculus when we took that derivative. Remember those properties of natural logarithms because they can help immensely when it comes to taking the derivative. So anyway, I believe that's our next to last example for this semester. So we have one more that we'll enjoy together. So let's cherish every moment with it, shall we? All right, one more.